Multiplicities of zeros. In a previous video, we talked about what a zero of a polynomial is. It's essentially just the x-intercept. We talked about a really important theorem that says that if you have a zero, if x equals c is a zero, then x minus c is a factor of a polynomial. And we use that to construct a polynomial when we were given the zeros. We'll be doing the opposite direction, taking a polynomial and getting it zeros, and then we can talk about multiplicity too. So the multiplicity of a zero is the number of times that the zero is repeated. And essentially that means the exponent on the factor that the zero came from. So let's do a few examples here, talking about the multiplicities. I'm going to rewrite the theorem that we had in a different order. If x minus c is a factor, that means x equal to c is a zero. This is just the reverse order of what we had written before, but it means the same thing. So here, the way that I'm going to find the zeros and their multiplicities, I'm going to take this apart into the different terms. And then you're just, for each factor, taking the opposite of what you see. So I have 1, 2, 3 factors. And here's really what's happening. If I were to set this entire thing equal to 0 and try to find out where y is equal to 0, I would set each factor equal to 0, and that would give me the zeros. So here's really what's going on is I would say x minus 1 equals 0, and that gives me x equal to 1 is a 0. For the third one, we would have x plus 2 is equal to 0. That's why x is equal to negative 2. For this first one here, 2x cubed is equal to 0. The only way that 2x cubed could be 0 is if x is equal to 0. So the zeros we have are x equals 0, x equals 1, and x equals negative 2. Their multiplicities are simply the exponents. So for 0, the multiplicity of 0 is 3. It is repeated 3 times. The multiplicity of 1 is 2 because that 0 is repeated 2 times. The multiplicity of negative 2 is 4 because that 0 is repeated 4 times. Looking at this guy here, you might think that there's you might think there's 5 factors that we have to worry about here. We had to worry about the 2x cubed before, so why would we not need to worry about the negative 3? Negative 3, if I were to set that equal to 0, there's no solution. So when there's just a number out front, that doesn't give us any zeros, but if there's an x out front, that gives us the 0, 0, as funny as that sounds. So if I take this first guy, this is going to give me a 0 of x equals negative 3. And the multiplicity, there's no exponent, so it's a secret 1. If there's no exponent, there's a secret 1, which means the multiplicity is 1. For this factor, x minus 4, the 0 is 4. And the multiplicity, there's no exponent, so it's a 1. For this factor, opposite sign, right? X equals negative 7 is the 0. Its multiplicity is 3. For this x squared plus 1 portion, this is actually a trick. You had seen how I said for each of these, you set each factor equal to 0, you would get the 0 from it. Well, if you were to try to set x squared plus 1 equal to 0, you wouldn't get any, you wouldn't be able to factor it. This doesn't factor, it never equals 0, it has no zeros. So sometimes you end up with these factors that just don't contribute any zeros. Technically, they're contributing imaginary zeros, but we're not getting into that. So if you were to ever end up with a sum of squares here, or a quadratic that doesn't factor, that would not contribute to your zeros. This would never equal 0 because if you were to plug in any number here and square it, it'll become positive. And then if you add 1 to it, you're going to be even more positive. So this will never equal 0. It's a sum of squares. This does not contribute any zeros. If you were to try to find a 0 from it, x squared plus 1 equals 0, x squared equals negative 1. You would take the square root on both sides, and you would get x equals plus or minus the square root of negative 1. And that's where the issue is. For all these other factors, you're able to, x minus 4 equals 0. X is equal to 4. X plus 3 equals 0. X is equal to negative 3. But it doesn't work with the x squared plus 1. That's a tricky one, but, we still talk about it. Find a polynomial of degree 6 that has the following zeros: negative 6 with a multiplicity of 2, 0 with a multiplicity of 3, and and who knows what. I meant to have another number here. Write in, I don't know, choose your favorite number. Let's do 4. Now, here's a fun fact. If you add up the multiplicities of all your zeros, it equals the degree of your polynomial. So we have 3 zeros, negative 6, 0, and 4. The factor for negative 6 will be x plus 6. And then because the multiplicity on this guy is 2, we're going to give him an exponent of 2. For 0, this would be x minus 0. And This guy has a multiplicity of 3. But that 0 doesn't do anything. The x minus 0 doesn't change anything, so this just becomes x cubed. We weren't told anything about the multiplicity of 4, so we can just assume that that's multiplicity 1. It would become x minus 4, and we won't put an exponent on him. So our polynomial, typically if we have a factor of just x, like this guy over here, x cubed, we put that out front. So we put the x cubed out front. Then we have x plus 6 squared, and we have x minus 4. If you were to add up the multiplicities, it's a bad box. If you were to add up the multiplicities, because this guy has a secret multiplicity of 1, 2 plus 3 plus 1 is 6, and that means that this polynomial has a degree 6. So the multiplicities are really just the exponents that we see on the corresponding 0. Now, the multiplicity of the 0 affects the behavior of the graph at that intercept. So if we have even multiplicities, here are some examples of even multiplicities. This would be a multiplicity of 2, this would be multiplicity of 4, this would be multiplicity of 6, multiplicity of 8. With all of these even multiplicities, notice that the graph just seems to kind of bounce off the x-axis. These zeros are at 0. So the zeros are all right here. What's happening is as that multiplicity gets higher and higher and stays even, it just gets flatter and flatter at the 0. So this guy's really flat. Well, this guy just kind of touches it. On the other hand, if we have a multiplicity that is odd, the graph is going to pass through the x-axis at that 0. So 1, 3, 5, and 7, notice that the graph at 0 passes through. It starts on one side of the x-axis, it ends up on the other. And additionally, notice that the higher the odd multiplicity gets, the more curvy it becomes at that 0. So it kind of like no curve at all, little curve, more curve, and then it's even flatter here. It really resembles what you're seeing up here in the even multiplicities. So this gives us some multiplicity rules. If we have an even multiplicity, this is going to bounce off the x-axis. Because again, maybe I should have repeated this earlier in the video. These zeros are x-intercepts. When I say 0, you want to be thinking x-intercept. So that's the reason I'm talking about here on the x-axis, because that's where its x-intercept is. So if something is a 0, that is where the function touches the x-axis. So even multiplicities are going to bounce off the x-axis. So you'd have either something like, if here's your 0, you'd either touch it and bounce up, or if you're coming from the underneath side, you would touch it and bounce away. On the other hand, odd multiplicities are going to cross through the x-axis. If you have a multiplicity of 1, there's not going to be any wiggle when you cross through the x-axis. So if your 0 is right here, you're just going to kind of pass through. On the other hand, if you have anything higher than 1 and odd, so 3 or beyond is what I have here, 3 plus. 3 or more. If this is your 0, you're going to wiggle. This is no wiggle. This is a wiggle. So if I look at these graphs down here, you can see that I have the graph and I have the factored form. So for this guy, we have x equals -1 is a 0. That's right here. And it has a multiplicity of 2. That's its exponent. Here we have the 0, 5, and it has a multiplicity of 1. Right. So those are the two locations of our zeros. You'll notice here at -1, the multiplicity was 2, so it came up, it bounced. And then when it hit the x-axis again at 5, it passed through. No wiggle. Sorry, my computer popped up. There we go. Right here, x equals -1, multiplicity 2. We had a bounce. Now, if we change things slightly, notice that the x plus 1 was kept the same, but instead of x minus 5 raised to the first power, it's x minus 5 raised to the cube. The difference here, no wiggle versus wiggle. Right, this one still bounces the way that it's supposed to. But this guy, instead of going straight through, he wiggle jigs. So all that is the same. All that is the same. The difference is this guy with the wiggle. This is almost identically the same. Just has multiplicity 3. So that is how multiplicities affect the graph of a function. We are going to put everything together in, well, I guess 2 videos. The next video is going to talk about how we know if a graph comes from the bottom and goes like, does it come from the bottom or does it come from the top? Or, what happens in here? How do I draw a graph given just its function? We're going to be talking about the which direction does it come from part in the next video. And in the following video, we will finally get to graphing. As always, if you have any questions, send me an email and I'm happy to answer any questions. Otherwise, I will see you in the next video.